All right, welcome back. So last time we talked about capacitance. I think we are pretty much done with all the content, but I just want to give you guys two more examples on this topic. So let's take a look on the examples right away. The first example here says you have two capacitors, each have conducting plates of surface area A and an air gap of with D. They are connected in parallel as shown in this figure, and each has a charge Q on the positive and negative charge plate. A slab that has a width of D and area of A, which is the same as the plate. And a dielectric conductor kappa is inserted in between the plate of one of the capacitors. Calculate the new charge Q prime on the positive charge plate of the capacitor after electrostatic equilibrium is re-established. Okay, so you have this dielectric insert into here. So originally these two are identical. They have the same amount of charges. Now, once you have this one goes in, right? So what happens is going to be, because if you have dielectric here, then the capacitance will increase, right? If capacitance increases, capacitance equal to charge over V. So charge is the same, but then capacity increase, so that means V changes. So if there's V change over here, then that means V on this guy and on this guy will be different. So then there will be rearrangement of charges, right? So charge will go from one plate to the another plate. So let's take a look on what will happen here, okay? So, but after this guy's inserted, right, you still would have the two plates in parallel, and after redistribute of the charge, the two should at the end should have the same voltage. So these two should be still in parallel, but the charge will be redistributed, right? So then one capacitor gains charge, the other plate will lose charge. So in that sense, so total charge should be still the same as the original. So originally each one has Q, so then total will be 2Q, right? But this guy capacitance changes, increased by kappa. This guy will be the same. So that means the charges will be different, but voltage will be different. So let's take a look on here. So we probably would calculate the voltage first on the two plate, right? Because we can calculate if once this gets in, we can calculate what will be the capacitance of this one. And once that's calculated, we can calculate what will be the V prime across the combination. Okay, that means the two will be share the same V prime. And once we have that, we can calculate how much charge is on this guy and then how much charge is on that guy if you want to look out for the charge on that guy too. Okay, so let's take a look on this. So the two are in parallel, right? So that means they are connected to the same, or if you measure the voltage, it's going to be the same, right? And this one over here, now this one has the dielectric inside it. Okay, so let's put that as dielectric. This one will be the original C0, okay, initial, and then this one becomes C, okay. So for C, because it's dielectric, so we know it's going to be kappa times C naught, right? And original C naught should be equal to epsilon naught times A over D. So A and D are given, so we can use those two. All right, so for the in parallel equivalent, then will be C plus C naught, okay? So that would be kappa plus 1, right? Times epsilon naught A over D, because this guy is kappa times C naught, and then this guy is C naught, okay? So that's your equivalent. So then V prime, the new voltage, or you can just say V. You can say the initial V would be V0. So then this would be V, okay? But let's just use V prime. So it'll be the total charge. This would be 2Q over CEQ, right? So it's going to be 2Q divided by this and then flip that. So 2Q over kappa plus 1, and then you flip this, okay? All right, so you have V prime now. You can calculate Q prime. Q prime will be C times V prime. So C is this guy or this guy here, kappa times kappa times that, so kappa times this, epsilon naught A over D. Okay, let's see. V prime is 2Q over kappa plus 1, and then D on top, epsilon naught times A. Okay, so there'll be cancellation, this, and that. Okay, so at the end, you get kappa divided by, or 2 times kappa divided by kappa plus 1 times Q. Okay, so that's your final charge on this plate, on this capacitor, the 2 plates of that capacitor. All right. Okay, so then the next one, it says find the capacitance of the parallel plate capacitor shown here. So this guy, the area, so 2 plates, and then there's combination of dielectric or insulators. Okay, so kappa 1 and then kappa 2. So these two are okay, let's put this. So the whole plate is divided into 2 parts over here, equal part, and then on the left part is equal, divided into two equal parts in addition, okay, or further down the row. So kappa 1 on top and kappa 2 on top. So then these two are connected one after another, right? So these two are then actually in series, and then this will be in parallel. So you can divide the whole thing into different parts, okay? So then this one will be having the configuration of like you have a 2 capacitors in series and 1 capacitor in parallel. So this is what you have. This is going to have. So this thing now becomes, or let me draw this one first. Okay, so A, and then divided into 2. So this separation is D, divided into 2 halves. Okay, so this guy, kappa, and then this one divided further into 2 more equal parts, kappa 1, kappa 2, and kappa 3. So this is equivalent to then a C1 and a C2, and that's in parallel with a C3. Okay, so that's why it is. So we're going to calculate these two first. They are in series. So C1 will be kappa 1 epsilon naught times the area of the plate. Now it's just half of it. So then the area will be 1/2 of the original. Okay, divided by distance. This is divided by 1/2 of the D. So 1/2 of the D. Okay, so in that case, so 1/2 and 1/2 actually cancels. So then this is going to be kappa 1 epsilon naught A over D. For C2, this is kappa 2 epsilon naught again, 1/2 of A divided by 1/2 of the D. So that will be kappa 2 epsilon naught A over D. Okay. For C3, okay, so it's going to be kappa 3, now 1/2 of A, and then epsilon naught in front of it, and then divided by the separation is DOD. Okay, so this guy will be actually kappa 3 over 2 epsilon naught A over D. Okay, so they are all like the multiples of epsilon naught A over D, epsilon naught over AD, right? So this part is the same, and this is the same. Okay. Okay, you can call that like epsilon naught, or C naught, which is the capacitor of the capacitor without any dielectric, right? Okay, so the two in series, so that means equivalent of that part should be 1 over C1 plus 1 over C2 and then inverse. Okay, so it'll be 1 over, let's call this as kappa 1 C naught, and this would be kappa 2 C naught. This guy would be half of kappa 3 C naught. Okay, so 1 over kappa 1 0 plus 1 over kappa 2 C0 and then inverse. Okay. So this will give you kappa 1 times kappa 2 over kappa 1 plus kappa 2 times C naught. Okay, and this guy in parallel, so then the final C equivalent should be just C equivalent prime plus C3. So kappa 1, kappa 2 over kappa 1 plus kappa 2 C naught plus kappa 3 over 2 C naught, which is equal to just kappa 1, kappa 2 over kappa 1 plus kappa 2 plus kappa 3 over 2, and then times C naught, where C naught is equal to epsilon naught A over D. Okay, so that's your final combination of these this capacitor. Okay, you divide them into 3. All right. So then we'll finish the chapter of the capacitor. Now let's move on to the next chapter. Okay, so on current and resistance. So first, look at the definition of current. So, in this case, electric current. So electric current is defined as the flow of the charge, electric charge from one place to another place over given time period delta t. So it's delta q over delta t. So this is average current then. Now for instantaneous current, you do take limit of delta t goes to 0, right? So then that means you are doing derivative of q over derivative of t. The current has the unit SI unit of Coulomb per second, which is C over second, or it has its own name called ampere, symbol A, okay, for that. So charge could be positive, could be negative. So then that means it depends on the charge carriers you have, the type of charge carriers you have. You might have positive charge carrier, you might have negative charge carrier. So if you have positive charge carrier, then the motion of the charge carriers are in the same direction as the current. If you have negative charge carriers, which is most of the case we have, as electrons, like the electronics, everything in it has the charge carriers being the negative charge. So current and then the movement of the charges are actually in the opposite directions. Okay. All right. So first example here, it says a conductor carries certain amount of current, and that is describing exponentially with the time. The current is modeled as I equal to I naught e to the minus t over tau, where I naught is 3.00 amperes. Is the current at time t equal to 0, and tau equal to 0.150 is the time constant. So that's a constant number. How much charge flows through the conductor between t equal to 0 and t equal to 3? Okay, so in this case, your charge is varying. And according to the definition, I equal to, okay, let's take a look on this together. So I equal to, right, the definition says if you are looking for average, right, average is delta Q over delta T. Okay, but in this case, I as a function of time is I naught e to the minus T over tau, okay? So this is instantaneous current. So that means you are looking for I equal to derivative Q over derivative T, okay? And it wants to calculate how much charge. So that means you are going to start with this. So then you're going to write dq equal to I times dt, right? And then you'll integrate them for the total q. So total q equals to integration of dq, and that's integration of this guy, I dt from t equal to 0. It says between t equal to 0 and 3 times of tau. 3 times of tau, that means 1.5 seconds because tau equals to 1.5. Okay, so you're taking the I naught e to the minus t over tau for this integration from 0 to 1.5 seconds, and dt. I naught is the constant number, so delta q then equals to I naught goes in front, which is 3.00 amps. Okay, integration of this guy. Integration of exponential function is again an exponential function, right? But there's this factor of there, so you should apply chain rule. So that means you integrate up, and then it becomes the there should be a factor of minus tau in front because that's minus of tau. So minus of tau e to the minus t over tau. Okay, and then that's from 1 to 1.5 seconds. So 3.00 amps. minus 0.5 seconds, right? Exponential of minus t over 0.5 seconds, and then from 0 to 1.5 seconds. You plug in the upper limits minus the lower limit, okay? So the upper limits will be like 1.5 over that gives you minus 3, okay? And then this now becomes 3.008 times minus 0.5 seconds times e to the minus 3. And when it goes to 0, right? So e to the 0. So that means minus. Okay, so the first term minus the second term, 0 0.0 seconds e to the 0, which is 1. Okay, so this become 1. And that's a minus. All right. So this gives you 1.43 coulombs, okay, for the total charge. All right. Okay, move on then here. So when you have a circuit, so the current typically goes from the positive terminal of the power supply, which could be a battery or a power supply, and then it goes through the circuit and comes back, okay? Typically, if you have LiPo, that's its symbol, and battery, so this means you have like two batteries in together, or sometimes you might have just like one big line and then one small line. That means you have just one battery. This is symbol for the switch, okay? Okay, next section on conduction in metals. So electrons for most metals are the charge carriers, so goes from one side to another side. Now, you probably realize that once you turn on the switch, then the light lit up right away, right? So it's actually not that the electrons moves at very large speed, but as one electron enters, another electron will exit at the other end of the whole circuit. Okay, so the movement of electrons itself, it's actually quite dramatic, and then comes back and forth because the electrons bump into atoms and then or nucleus and then other electrons. Okay, so it bounces back and forth, but overall it's going in one direction. Okay, so in the opposite direction of the current because electrons are negatively charged. So the average velocity here is called the drift velocity of the electron. Okay, so the drift velocity V sub d for that. So the current in this conductor then actually is proportional to the drift velocity. Okay, so to calculate, you do charge Q over a certain portion of that conductor. So take the length of the drift velocity of a charge carrier times delta T, and then you can calculate how much total charge is inside there. So Q will be the charge of the charge carriers, and will be the number density of the charge carriers, and the A will be the cross-sectional area, velocity times delta T, right? So this gives you the volume. So A times the length, okay, and then there will be volume, and then times the density, that gives how many numbers, times the charge of each one gives you a total charge, okay? And then divided by delta T will be your current. So QMAV D. So I is proportional to the drift velocity, okay? And also proportional to the cross-sectional area, proportional to the number density of charges, and then proportional to the charge of the charge carrier, each individual charge carriers, okay? And if you do current divided by the cross-sectional area, then it's equal to QMVD, okay? So this is called current density, right? It's current per unit area. So current density or current actually has directions, so you can call them as vectors. So current density should be a vector, okay? And at certain moment, because electrons are moving in random direction from time to time, so you might expect like current density not necessary to be in the same direction or normal direction of the cross-sectional area, okay? But when you calculate and the current, it's overall will be going to in that direction because there's cancellation from others. Okay. So if you have an uneven cross-sectional area like this, a random one, if you are going to calculate local current density or current in that sense, then you'll be doing integration. You divide the surface into small patches, and then you do integrations through the whole surface. Okay, so integrations through that, okay, to get the total current through that particular surface. All right. Okay. So the next two sections, I feel like they are closely related to each other. So Ohm's law and resistivity and resistance. So it has been demonstrated that the voltage and current are proportional to each other through a conductor. So then if you do V over I, it gives you R, or you do I times R, that gives you V. So V equal to I times R. So that's basically Ohm's law, or R equal to V divided by I, okay? So R is the resistance of the conductor and has a SI unit of ohms, which is equal to 1 volt divided by A, okay? Now, Ohm's law is for most conductors, but it's not universally applied to any materials, okay? So like the other conductors, like semiconductors, okay, in that sense, they probably will not obey Ohm's law, okay? So just keep that in mind. It's not universal. It applies to most metallic conductors, okay? All right. So the conductors have resistance, okay? So that means it actually has resistivity, as the name implies, so to the current. So that means it's not going through like freeway, right, in a sense for the charge carriers, but the charge carriers will encounter some resistance there. So the property of a material, its resistance, called resistivity. So resistivity for certain materials, that's a fixed number, okay? So it's proportional, or we call it actually rho for resistivity, and resistivity is proportional to resistance, okay? To calculate resistance, that's equal to resistivity times the length of the material divided by the cross-sectional area, okay? So R is proportional to the resistivity, proportional to the length, and then inverse proportional to the area. So you can imagine if the material is longer, right, then charge carriers bumps into more atoms or other charges. So then the longer that is, the more resistance that material would be. And then if you have wider, right, this is like highway, you have more lanes, then the traffic is low. So in that sense, if we get the smaller resistance. All right, resistivity has a SI unit of ohms times meters, okay? So according to this equation here. So for different materials, it has different resistivities as shown in the figure here. So most metals are having very low resistivity, so they are used as conductors, like the for the electricities, right? So for electricity to deliver from the power plant to the household, so there's in between we use metals for as conductors, okay, in that sense. Insulators have a very large resistivity, okay, and semiconductors in between the metal and insulators. All right, take a look on this example here. It says a current of 0.86 amps flows through a copper wire of 0.74 millimeter in diameter. When it connects to a potential of 15 volts, how long is the wire? All right, so we just learned that the Ohm's law and related to resistivity. So let's take a look at that. So it tells us the current, okay, current I equals to 0.86 amps. The length, the copper wire has diameter of 0.74 millimeters, so 0.74 10 to the minus 3 meters. Voltage, 15 volts, okay? It's asking you how long is the wire. So Ohm's law will tell you how to calculate resistivity, resistance, right? And then resistance is related to resistivity and length in that case. So it looks like we can calculate this, and then we can calculate this given the diameter, right? So this will be calculated, this will be calculated. And then for this resistivity, it tells you this is copper. So you can look up for copper for that. Okay, then you can solve for that guy. All right. So let's say V over I equals to then rho L divided by A, right? So then L equals to V times A over I times rho, okay? So V is 15 volts, I is 0.86 amps, or A, sorry, that's not I. Should be pi over 4 D square, 0.74 times 10 to the minus 3 meters square, okay? So that's the area. Times the area divided by 0.86 amps. And the resistivity, if you go one more slide up, you'll find it for copper, this is 1.68 times 10 to the minus 8 ohms times meters, okay? So that tells you 446.5 meters is the wire, okay? That's the length of the wire. All right, so let's go back to the slide. Okay, so resistance is related to temperature. So I think we have learned that, or actually used that in the lab of the thermal expansion, right? We measure resistance and then we actually relate it to the temperature. So in general, the resistance of material goes up as the temperature goes up due to thermal effect, okay? But for semiconductors, that's another story. Okay, so it actually decreases with the increase in temperature due to increasing of free electrons. Okay, and normally resistivity decreases as temperature decreases. But for certain materials, one particular one is called superconductor. When temperature drops to a certain point, then it becomes non-resistive. So that means it has zero resistivity. Okay. So this is the temperature effect of the resistance, or the resistance related to temperature for the material. So it goes up normally, okay, as resistivity goes up. And alpha here, you calculate alpha, which is called temperature coefficient of resistivity, is equal to rho minus rho naught over rho naught divided by T minus T naught. So if you have a starting point, okay, then you can calculate that. So rho naught is the resistivity at temperature T naught, and rho is the resistivity at temperature T. Okay. So when you look at resistors, most often you'll find color codings. So some of them have 4 bands on the colors, and then some of them have 5 bands. So we have done this in the lab, but according to the numbers, so the first two here, so if you have 4 bands, so 3 will be closer to each other, and then 1 will be further away. And then if you have 5 bands, the first 4 will be close to each other, the last one will be further away from those. So the last one is the tolerance. So you look at the color of the last band, and then you look it up here. Okay, so for this guy, the gray or silver here is 10%. So that means it's whatever these 3 gives plus minus 10%. So for the 3 here, 3 digits here. So the first one is the first 2 are the digits. So whatever you get, write down the number. So for this guy, orange, so you are going to write like 3, and then black means 0. So you're going to say 30. And blue, that is the multiplier of times 10 to the power. So blue stands for 6, so 10 to the 6th power. So this is 30 million ohms for this guy. Okay. All right. For 5 bands, you have 3 digits code and then a multiplier. Okay, so similar to the 4 bands. And this is another example. Okay, so you can take a look at this example yourself. Next, let's quickly take a look on electric energy and power. Okay, so when a charge moves across a power potential, then there's a power change, right, for that charge. So the power change is equal to the charge times the voltage change, that V. So then if you do power, or the change in energy delta U over delta T, that gives you power. So then that's this guy divided by that, okay? So that tells you it's delta Q over delta T times V, but delta Q over delta T, that gives you I, right, according to the definition. So then electric power can be written as the current through the conductor times the voltage across, okay? And that's power, so it's in units of watt, okay? So I times U. According to Ohm's law, so V is equal to I times R. So power then also can be equal to I squared times R, or I can be written as V over R. So then power can also be written as V squared over R. Okay, so power equal to I times V or I squared times R or V squared over R. Those three expressions. Just remember, power mostly becomes heat inside the resistive material. Okay, so in that sense. Okay, let's take a look on this one here. So this one says a 65 volts generator supplies 4.8 kilo watts of power. How much current does the generator produce? Okay, so this is a pretty simple one, right? So power equals to I times V, or I square R, or V square over R. It tells us power, and also V is looking for I. So we are going to use that, right? So I then equal to power over V. Okay, so pretty simple. 4.8 kilo 10 to the third divided by 65 volts. So that gives you 74 amps on that one. All right. So let's go back to the slide. Now let's take a look on superconductivity. Okay, so normally this happens. So this was first discovered about a century years ago. Yeah, a century ago, 100 years ago in a sense, on Mercury. So as the temperature drops down, and all of a sudden the resistance of Mercury goes to zero. All right, and so that happens to different materials. Normally, this is a very low temperature, like 4.2 Kelvin, right? So it's very close to the absolute value. Now, these days, we over almost 100 years of development, now the temperature, that the critical temperature here for materials. So we are looking into like new materials. So for some materials, now it's called like high temperature superconductor. So those are in the orders of 100K or sometimes close to 200K. Okay, so there's a lot of improvement in that area. That's this video for you guys to watch yourself. So it's a pretty amazing one, that how material can be floating in the air because of the superconductivity. Okay, so we'll stop here today, and then we'll come back another time. So see you guys. Bye.